Hello everyone. This video covers the practical exam from May-June 2024, paper 32, question 2. If you are looking for advance your lab skills, stay with me and I will do my best to share how to answer this practical. Materials and apparatus setup for question number 2. All the materials for this lab are laid out on the bench, and you need to follow the lab instructions to set everything up. In this picture, you see the apparatus already assembled, giving you a clear idea of what's needed to complete the experiment. Let's begin by focus on the wooden rod with 3 string loops. These loops need to be attached to the spring, to a cork, and a hanging mess. You need 2 flat-headed nails attached to corks, 2 split corks, 2 lab stands, 2 clamps. The clamp looks like this one. 100 grams mass hanger and 100 grams slotted mass. 15 centimeters plumb line with a bob, and some additional materials not shown in the picture. 100 centimeters and 30 centimeters rulers, a triangular prism, looks like this, 180 degrees protractor with 1 degree divisions, a stopwatch reading to 0.1 seconds or better. Question 2. In this experiment, you will investigate the equilibrium of a wooden rod. To set up the apparatus, it probably will take 10 minutes. Please take your time to set up correctly before measuring. There are 2 conditions. The first one, the wooden rod must be parallel to the bench. And the second condition, the spring must be in the vertical position. Now the first task in this lab is indicating the distance between the ends of the spring is LO, as shown in figure 2.1. So this is LO. Measure and record LO. So we measure, and LO in our case is 0.135 meter. So the mark scheme shows the value for LO to nearest millimeter and in range 0.05 to 0.2 meters. One important note for all practical exams is when measuring in meters, centimeters, and millimeters, the number of decimal places generally depends on the precision of the instrument. For example, for meters, for measurements with a precision of 1 millimeter, it's common to write measurement to 3 decimal places. In centimeters, it's common to write measurements to 1 decimal place. And for millimeter, no decimal places are usually needed. This table provides a summary of how to properly express your answers in meters, centimeters, and millimeters. Now, pull the mesh hanger down a short distance and then release it. The mesh hanger will oscillate. You might need to flip the base of the lab stand before pulling the mesh hanger down to provide additional space for vertical oscillation. The 2 marks for this question suggests that you show evidence of 2 trials with at least 5 oscillations. I prefer use 10 oscillations. The reason is because short time measurements often introduce random errors due to experimental reaction time with the stopwatch. To reduce this, follow these steps to calculate the time for one oscillation. To secure your marks for this question, let's create a data table with 2 trials and an average. Then measure the total time for 10 oscillations for each trial. Then divide each trial's time by 10 to find the time for one oscillation and average. So here is the period. The period is the time for one oscillation. So make sure to write the answer with the correct unit, which is seconds. Let's use this data table with the given values. So we have here alpha and the period, which is the result from question AI, 0.54 seconds. After equation substitutions, the value of K, the spring constant, is 27 Newton per meter. So now is asking to justify the number of significant figures that you have given for your value of K. So the lab script provided the equation for the spring constant. And the values are, for alpha, we have here 3 significant figures. And for the period, we have 2 significant figures. If you need to update your skills about significant figures, you can pause this video and read this slide where explain how we are going to determine that K has 2 significant figures. So here is my answer. Based on this equation, the value of K is 27 Newton per meter, with 2 significant figures. It's consistent with the least precise measurement, which has 2 significant figures. Although alpha has 3 significant figures, the final result for K is determined by the precision of T. Question B. Move the stand supporting the spring away from the other stand and add the plumb line, as shown in this diagram. And this is the real picture. Adjust the apparatus so that the angle data between the spring and the vertical is approximately 20 degrees, and the wooden rod is parallel to the bench, as shown in this diagram. The new distance between the ends of the spring is L, as shown in this diagram. Measure and record L. So L in this case is 0.140 meter. The answer is with 3 decimal places. Now measure and record the angle data. So 20 degrees. Next question. Estimate the percentage uncertainty in your value of data. Show your working. To estimate the percentage uncertainty in your value of data, consider the challenging conditions such as poor visibility, including lack of contrast, as shown in this picture, which makes it difficult to see the protractor marks. Additionally, consider the difficulty of keeping the protractor steady without disturbing the apparatus. Here are the guidelines to answer this question. First, check the smallest division on the protractor, which in this case is 1 degree. Second, given the poor visibility and the challenge of holding the protractor steady, it's reasonable to increase the estimated uncertainty to account for potential reading errors. You may add plus minus 2 degrees or plus minus 3 degrees to reflect these conditions. And the last one, I personally chose an uncertainty of 3 degrees because I found difficult to keep the protractor steady without accidentally moving the spring. Next, adjust the apparatus so that the angle data between the spring and the vertical is approximately 45 degrees and the wooden rod is parallel to the bench. So the new length is 0.155 meters and the angle is 45 degrees. So now we have here 3 marks. According to the mark scheme, the 3 marks are distributed between the value of L, the value of the angle, and this second value must be greater than the first one for the 20 degrees. Question C. It's suggested that the relationship between L, the length of the spring, and the angle is given by this formula, where B is equal to 2 newtons and D is a constant. Using your data, calculate the two values of D. In this table, I have organized all the values for corresponded to D1 and to D2. So the first angle was 20 degrees. The length of the spring was 0.14 meters. The initial length, without separating those two lab stands, originally was 0.135 meters. The value of K is 27 that we calculated previously, and the value of B, 2 Newton, was given. So the same goes for D2, 45 degrees. This is the value of the second length of the spring. This is the initial length of the spring. This is the value of the spring constant because it's constant. And this is the value of B. So this is the original equation that was given in this question. I'm going to rearrange this equation in terms of D. So now D is equal K, then multiply the difference between the lengths plus B, all these times cosine of theta. So now in this table, I show here the substitution for the equation for the values that I have in this table right here for D1 and for D2. So then I have like the result of all this is 2.135 times cosine of 20 degrees, and the result of all these is 2.54 times cosine of 45. My final answer for D1 is 2.01 and for D2 is 1.79, each one with 3 significant figures. However, I don't have the unit, so you need to figure out what is the unit for D. To determine the unit for D, I have organized here in this table all the variables that they are involved in this equation. So the unit for the angle is degree, which is actually is not a unit. For length is meter. For initial length is meter. For the value of the spring constant is Newton per meter. And the value of B is in Newton, was given in the question. Now, in this slide, I'm showing you the unit substitutions for K, Newton per meter, for L, meter, for initial L or L always meter, B is Newton, and cosine of theta. Now in this step, understand that m minus m is not 0. This is just a recombining units. So this is going to result in a value which is in meter. So this is exactly what I did. I did not include cosine of theta because there is no unit. So now we are in this step. So Newton per meter, I know this is a negative exponent, so I just did in fraction. So times meter plus n. So here cancel both meters. And in conclusion, the unit for D is Newton. Now I can write the first and second values for D with the unit, which is Newton. Question D. It suggested that the percentage uncertainty in the values of D is 10%. Using this uncertainty, explain whether your results support the relationship in C. So the first value of D is 2.01 Newton. The second value of D is 1.75 Newton. The calculation of percentage difference between two values is given by this formula. The percentage uncertainty of D will be D1 minus D2 divided by D2 times 100. Now I'm doing value substitutions here. The value of D1 is 2.01 newtons, D2 is 1.79, and all these divided by D2, 1.79 times 100. So the percentage difference between two values is 12.29% or 12%. And as my answer, since the percentage of uncertainty of D is 12%, is greater than 10%, then the results of D1 and D2 do not support the relationship of the equation of question C. The final section of this lab practical is worth 8 marks. In this part, with 4 marks, you need to identify and describe 40 steps from the lab that could be improved. The next 4 marks, You need to describe 4 improvements that could be made to this experiment. You need to suggest a solution or propose improvements to enhance the accuracy or effectiveness of the procedure. To make it less complicated, I have organized my improvements in a table format for easier presentation. While I have listed 5 items, only 4 are needed for this section. So let me start by writing my first limitations or problems that I found in this lab experiment. So this is kind of standard for all practical 2. If you can memorize, it's a good idea. 2 readings for L, in this case L, are not enough to draw a valid conclusion. As improvement, take more readings of L and plot a graph. Let's go to the second problem. Difficult to measure the period T when deciding end or start a complete oscillation. As a solution for this problem, use marker placed at midpoint of the oscillation and record a video with a timer to view frame by frame. Third one, difficult to measure the length of the spring L or LO, the initial length, when holding ruler is steady next to the spring which moves when touched by the ruler. As an improvement or a solution, improved method of measuring the length L or LO by using a clamp to support the ruler next to the spring. Fourth problem. Difficult to ensure wooden rod is parallel to bench, or difficult to ensure that spring is vertical. As a solution for this problem, measure from rod to bench at both ends to ensure it's parallel to the bench. Last problem. Difficult to hold protractor is steady. As a solution, hold protractor with a clamp. So, as a conclusion of this table, number 1, problem and solution, number 1 and number 2, are standards for question 2. So if you want to memorize both, I think is a good idea. And the second point is that you need just 4 sources of uncertainty or limitations and 4 improvements for each problem that you are writing. You are talking about, you need to talk about a problem, you need to find a solution for the particular problem. Here we are. I have reached the end of this practical. Please leave your suggestions or feedback on my solutions in the comments section. Unfortunately, there are limited online resources available to guide students through AS physics practicals, and the mark schemes are often vague and not very detailed. Thank you for staying until the end and let me know if this video was helpful.